Hey guys, welcome back to my YouTube channel. Today I'm gonna explain about graph and about rectangular crossing number. So let's get started. First one is about graph. Graph theory was first introduced by Leonhard Euler, a Swiss mathematician, in 1736 through Euler's writings, which contained the problem-solving efforts of the Königsberg Bridge, which was very famous in Europe. What is a graph? Usually when someone talks about graphs in mathematics and computer science, they are referring to something like this. 1. Graph. What we have are vertices, also called nodes, shown as the colored dots in these images, connected by edges, shown as the lines in these images. There can be any number of vertices which may or may not be connected by edges. If every vertex is connected to all other vertices, then it's considered a complete graph. 2. Complete graph. A bipartite graph is one in which each vertex belongs in one of two sets, and vertices of the same set are not connected by an edge. This is usually shown by coloring the vertices, that is red and blue, where red vertices can't be connected to other red vertices. 3. Complete bipartite graph. Depending on how the edges and points are drawn, you can create various types of graphs. Some examples include on the plane with straight edges, rectilinear, a graph containing no cycles, tree, all vertices on a line with curved edges, book embedding, or in some other space. 4. Two-page book embedding. One important thing to note is that moving the vertices of a graph only changes the appearance of the graph, but it's still the same graph. The crossing numbers of graphs is an interesting topic in discrete geometry, graph theory, graph drawing, and computer science. Though simple at its core, it lends itself to ideas that are much more complex. In graph theory, the crossing number G of a graph G is the lowest number of edge crossings of a plane drawing of the graph G. For instance, a graph is planar if and only if its crossing number is 0. Determining the crossing number continues to be of great importance in graph drawing, as user studies have shown that drawing graphs with few crossings makes it easier for people to understand the drawing. The study of crossing numbers originated in Turin's brick factory problem, in which Paul Turin asked for a factory plan that minimized the number of crossings between tracks connecting brick kilns to storage sites. Mathematically, this problem can be formalized as asking for the crossing number of a complete bipartite graph. 2. The same problem arose independently in sociology at approximately the same time, in connection with the construction of sociograms. 3. Turin's conjectured formula for the crossing numbers of complete bipartite graphs remains unproven, as does an analogous formula for the complete graphs. The crossing number inequality states that, for graphs where the number E of edges is sufficiently larger than the number N of vertices, the crossing number is at least proportional to E3/N2. It has applications in velocity design and incidence geometry. Without further qualification, the crossing number allows drawings in which the edges may be represented by arbitrary curves. A variation of this concept, the rectilinear crossing number, requires all edges to be straight line segments, and may differ from the crossing number. In particular, the rectilinear crossing number of a complete graph is essentially the same as the minimum number of convex quadrilaterals determined by a set of endpoints in general position.